Today I will teach you about fluctuation, which is in statistical mechanics. So first we have to know what is the fluctuation. Fluctuation is deviation of something's value from its average value. And we can measure this fluctuation by mean square deviation. Mean square deviation of any function a is defined by the average of the difference between an individual measure of a and its average measure. Now, we can write the average value of a in this way or a bar in this way. Now, mean square deviation we can write in this way. So, S square average minus A average square. So, in this way we can measure the mean square deviation. Now, we will calculate the fluctuation of energy. Fluctuation of energy. For this, we shall study fluctuation in total energy of a closed system in thermodynamical equilibrium at a given temperature. Such a system can be represented by a canonical ensemble. Now we will calculate the fluctuation in energy in this way. So we know the partition function for canonical ensemble is Z. Generally we denote partition function by Z. Z equal to summation over R e to the power minus ER by KT. And mean energy is, we can write in this way, E bar equal to summation over R ER e to the power minus ER by KT divided by summation over R e to the power minus ER by KT. Or we can write it expectation value or average value E and multiplication e to the power minus ER by KT equal to summation over R ER e to the power minus ER by KT. Now we will take differentiation of both sides of these equations. So if we take differentiation, we will get So we are getting this if we take the differentiation of this equation. Now we will rearrange this equation a little bit, then we will get summation over r a r square e to the power minus e r by kt divided by summation over r e to the power minus e r by kt minus e average value and summation over r er e to the power minus er by kt by divided by summation over r e to the power minus er by kt. So this equal to will be right hand side will be kt square del E average by del T. So the first factor on the left hand side represent E square average and the second represents E average square. So this first factor represent E square average and second factor represents E average square. So you can write it in this way: E square average minus E average square equal to kt square del E average by del T. But we know E square average minus E average square equal to E average minus E square and then average over all. So we can write, comparing this both of these two equations, we can write E average minus E square and average over all of these equal to kt square del E average by del T. Now when n is large, n is the number of particles. When n is large, then we can write E nearly equal to E average. So we can write E average minus E square average over all by E average square equal to kt square by square del E average by del T equal to kt square by square to Cv, where Cv is specific heat at constant volume. So we know Cv equal to Nk and E equal to Nkt. Therefore we have del E by E expectation value square will be kt square by n square k square t square into nk equal to 1 by n. Therefore, del E by E average value is of the order of n to the power minus half. Therefore, the standard relative deviation from the mean value is of the order of n to the power half. So, if we think for n equal to 10 to the power 22 fluctuations in energy will be very small. This, on the other hand, implies that the probability distribution in E in an ordinary thermodynamic system consisting large number of molecules is extremely sharp.